All right. As often, fewer of you come every class. Did people manage to get the assignment done before last night? Anybody have trouble with it? People are not necessarily saying. All right, so after class here, two people were struggling with one of the questions, and in my usual addiction, I spent until I thought I quickly made some changes to my slides on the knapsack problem and send them to you, but I didn't get them done until after midnight, so that was a moot point. But if you're struggling with recursive backtracking, what I changed in the code on the slides were, instead of doing a number of problems all at once, I did one and then changed them. I think it made it look earlier. Any other questions? Anything we need to be worrying about now? I think we're all right. So we're doing data structure invariance. All right. So if you remember, our data structure is going to have things that are hidden. So the public statement about a stack is that you stack up plates and you put things on top, right? That's what the outside world knows. But inside, we're going to have various invariants. And the invariant we're going to have for a linked list is that it looks like the linked list there, all right? And who do you have access to is pointing at the first one, right? And so that's going to be the top of the stack. See, we have first gives us access to the top of the stack, right? But you'll notice we have very little access to the bottom of the stack, which is fine because stacks don't access the bottom, right? All right, so what we have to do is we have to establish these invariants when we create the stack and maintain them every time somebody does a push for a pop. So when you create the empty stack, then I guess we're going to be a little bolder here because we're going to do queues as well. So queues need access to both ends. So here's there's the picture up at the top is our loop invariant, is a linked list with two pointers, one at the first and one at the last, right? And so what does the empty stack or queue look like? Well, it has no nodes whatsoever, so there's nothing to point at, so it just looks like this, all right? I've seen people writing code where they never let the thing be empty. They always have at least one thing in there because they get nervous about the empty pointer. And I'm saying, don't get nervous about the empty pointer. It usually works out fine. All right? All right, so now we need to maintain the loop invariant. All right, so we fly in from Mars, and what do we know is that the stack is running like it's supposed to, right? There it is, it's running like it's supposed to, and somebody comes along and pushes, so the invariance for so the precondition for that push is true, which is they're giving us information that we're going to push, right? And then what do we have to ensure after the code is, one, that we do what the push requires, which is that we push that object on the top, and that we maintain the system invariance, right? So what should the picture look like? You draw what the picture should look like, right? Everybody agree with this? So it's as I say, it's useful to draw the before and after picture, because what we're going to do is write code to get from one to the other, right? And so here's kind of step by step what we're doing. All right, so let's get here the code. So first, in the first little picture, we have to allocate space for the new record, and we do that with new temp. All right, so temp is just where yeah, so I guess temp is that really all you have to do? I thought you had to say temp equals. Is this Java? It's not Java. Somehow we got over to Python. Sorry for that. So in Python, you say what? You first have to say that temp is of type node, and then you have to give it a value by saying you call the node construct, right? All right, so somewhere I have to see if I have the Java code somewhere. All right, so that's what we get this guy here. And then we have to point the pointer up to the first guy. All right. Oh, first we put the information, then we put the information into this guy, right? Temp dot info is the info that we're putting in, right? And then we have to link up the link. So temp dot link gives you this spot there. And what do we want to put in it? We want to point it at this. And who's pointing at that? First is pointing at it, right? And then we have to get first to point at the new guy. Well, temp is pointing at the new guy, so you do this. All right, everybody good? It's not too bad except for that first line. All right, so everybody good with that code? All right, so you should always write the generic code for a generic sort of situation, but then you should see, does it work in all weird situations, right? And so one weird situation is when when the queue's empty, right? So if you run this code, you'll see we first get temp to point at a new thing, and then we get temp.link to point wherever first is, which is to nothing, which is fine because it's the last guy, right? So the last guy is supposed to point at nothing. And then we get first the point where temp is pointing, and it works just fine, right? Any questions about that? Everybody good? Oh, now it doesn't work quite fine. Maybe, in fact, this is why I stuck it in there, right? What about last? Last is still pointing at nil, right? So we should put in some extra code that says, hey, if last is pointing at something already, we're happy. But if last is pointing at nil, it should point at temp. Right? Does that make sense? You put in extra if statements to handle the funny cases. Good. Everybody back there, good? All right. So now what about the pop? The same sort of idea that, we have that the invariant is true, and then we call pop, and we need the postcondition of pop to be true, which is it returns the value at the top, and that the value's gone, and it still needs to have the invariant, right? So we can not panic, and what do we do? All right, so I guess first we're having a new variable called kill node, which is like Kill Bill, I guess, the guy you're going to kill, and you point it at same where the first item, right? Because first is pointing at it. And then you get first to walk along. Remember, we did walk code. So first equals first link. So first is now going to point where first link is pointing, moves you along. And then we take the information out of the node we're killing, right? Then we free up the new node, which in Java you don't have to do. And then you return the item. Oh, there's a bug in here too, since this is info and this is item. Everybody good? All right. And now, if the stack is empty, you can throw some sort of exception, right? But if it has one node, we want to make sure that it still works. All right. So with one node, what do? Is we point kill node to the first node. We move first to where the node is pointing to, right? First walks along. So first is going to get the value nil, which is great. And then, again, we take the information and kill it. Now, everybody see the problem that we have? Again, we have a problem with last, right? So last is still pointing at the thing that you're wanting to kill. So what can you do? You can say, right, if first is now empty, if first is now pointing at nil, then last should point at nil too. Yeah? Yeah, so first is pointing at the object, and then when it walks along, it's pointing at nil, right? So here we have this picture where first is pointing at nil, but last is still pointing at the thing that you killed, right? And so what can we say? How do we detect that this is a problem? Well, if first isn't pointing at anything, then last should point at nothing too. They're both nil. Yeah, does that make sense? The push? The one before was the other way. We were pushing things. Oh. That's the same one, right? Here, when we, is this the pop? Oh, this is still pop. I don't. Oh, last, in this one, we're popping off the first guy. And what's last doing? Last is way down, doing last sort of things, right? The only time we need to change, if the list is long, we only need to change last when the last item changes, right? All right, so now we can say, if we're doing a queue, right, we have to add things to the other end. All right, so how do we add something here? I guess I'm saying it's homework. It's not very hard, right? All right, how about removing the last item? All right, everybody think about how you remove it. You can get to it through last, right? You can kill it through last, right? But what's the hard part? Yeah, where does last point to, right? Where do we want it to point to? The second last, right? How do we point at the second last? How can you find the second? We got the last guy. How do you find the second last guy? Well, -1, it's not an array. They're not in order. These nodes are all willy-nilly throughout the universe, right? Yeah, so you could say, let's solve the problem by pointing at the second last, all right? But then when we delete the last one, the second last has to point to the third last, and you haven't really solved the problem, right? Exactly. Exactly. It's not so easy because you have to walk there from first. All right? So the other operations took a constant amount of time independent of how long your queue is, right? But this one's going to take order in time to get there. All right? All right, so here's a little table, right? If you want to, at the beginning of the queue, right, you can add and remove in constant time. From the end of the queue, you can add in constant time, but removing takes a long time, right? So how do you implement a queue? How do you implement the stack first? You do this. How do you implement a queue? Right? Right, that is a stack, right? What's a queue? That's a queue, right? People see that? All right, we could make this more fancy. We can have a doubly linked list. And what's this? Every node points to the guy before and the guy after, right? And the advantage of that is then from the end, you can walk backwards, right? And that allows you to do this in constant time too, right? Right, everybody good? All right. All right, I thought we did walking already, but let's walk. All right? So now what we're doing is we have this, and we're trying to say, let's insert an object somewhere in the middle. Yeah? What are you trying to do? Yeah. Yeah. Yeah, exactly. Because you can take the last and you can find the second last by walking backwards one step. All right, now we want to get here and we want to insert, right? And you can walk forwards with, only one foot, but then it's hard to, as you go forward, you lose things, right? And you can kind of do a look ahead with one pointer, but let's do 2 pointers. All right, we have 2 pointers, and what our goal is to have the 2 pointers sandwich the spot that we want to put things, right? We want to put it here. So what we're doing now is trying to get previous to point at what's going to point at 6, and next to point at what 6 needs to point to, right? So how do we do that? How do you get there? You're going to walk, right? How do you walk, right? So again, we need a loop invariant. What's going to be true in the middle? And what's going to be true in the middle is that we've walked part way, right? So how do you initialize this walk? Well, you could, right? You could sandwich, I guess if we're saying we sandwich the spot before the first node, right? See here we're sandwiching, right? If you go back, wind it. Sometimes when you think about the loop invariant, and then you go back in time, and you see what happens, right? We could have started with previous looking at 1 and next looking at 2, but that assumes that it's harder to set up, assumes that you have 2 nodes, right? This only assumes I have 1 node, right? I guess it still assumes I have some nodes, but you can see that it's sort of already going, right? So then how do you make progress? Well, you take a step. So we go from 2, 3 to 3, 4. Right? Everybody good? So we're going to walk down the list, maintain these 2 pointers until desired location is found. And so here's some code, right? Is that? We don't really got code here, but when do we want to, let's forget the exit condition. Let's talk about the walking condition, right? So to walk, you have previous and next. Previous can come to next, and the next can take a step, right? Everybody good with that? And when do we want to stop? Well, you don't want to fall off the end, right? If nil is pointing at nil, sorry, if next is pointing at nil, then you'll crash on this line, right? So we want to stop then. And we also want to stop if next info is bigger than our new element, right? If next is passed, we want to stop, right? Anybody know how an OR operates? Remember, an OR, only one of the things needs to be true, right? So what happens which one does the computer do first, right? I mean, here's a question. Suppose I got this OR here. What happens if I switch this line and this line, right? It doesn't change the logic at all, but what changes? Exactly. So if we did this first and next was nil, it would crash here, right? But if we check this first, if it's nil, it never does this, right? If you didn't know that, it's a good thing to know, right? And all right. All right, so here now we've sandwiched the spot, and we want to put it in where it belongs, right? So here we have Python code for getting a new variable temp. I guess temp will be pointing at this new guy, and temp info will be the new item, and then previous link needs to point at the new item, and then temp link needs to point where next is pointing, right? Everybody see it gets us from that picture to this picture. Are people good with these things? If I'm not mistaken, the next assignment is on pointers, right? All right, learning outcomes. All right, so what are learning outcomes for you need to understand contracts between different systems, data structures. You need to understand loop invariants and how to think about iterative algorithms, how to establish and maintain the loop invariant. various weird boundary conditions versus typical case, guarantee your code terminates, prove that the loop, right? Loop invariant plus exit condition gives the post condition, and think about running time. Everybody good?